Okay, this is the third hour of Physics 1C for, what's today, the 27th? Just closing some of these windows. They're all making noises right now. Okay. This is the second hour of Physics 1C for September 27th, third hour, final hour, for September 27th. And we're going to continue talking about electric potential. We're going to look at some examples, and eventually we'll look at the connection between electric potentials and electric fields that you can find using something called a gradient. All right, so we just defined that the electric potential due to a point charge was equal to kq over r, and these next two problems are going to use that definition to look at just ways in which we can apply that. So this problem right here, we want to find the electric potential due to 2 point charges. So we've got 2 point charges, q1 and q2. They have the same value. One's 12 nanocoulombs and one's negative 12 nanocoulombs. They're placed 10 centimeters apart. We had a problem like this in the previous chapter, but we were finding electric field. It's important, especially coming up on the test, that you can distinguish between the concept of electric potential and electric field. They sound similar, but they're different. This is potential. Electric field is the one that has the r squared in the denominator. All right, so what we're going to do now is we're going to look at these two charges. We want to find the electric potential at point A. So that's going to be equal to the electric potential from Q1 plus the electric potential from Q2. So that's going to be V1 plus V2. So that's going to be equal to K times Q1 divided by the distance from point A to Q1, which is 6 cm. So I'm just going to write down here 0.06 meters. Plus for V2, the distance between here and here is 0.04 meters. So we'll write K Q2 over 0.04. And then we just plug in our numbers. I think by now you all know what K is. Do I need to keep writing it over and over again? To save time, I'm not going to write it. Q1 is positive 12 nanocoulombs, so that's 12 times 10 to the negative 9 coulombs divided by 0.06 minus Q2. No, I'll put in the numerator. For Q2, we plug in a negative sign because it's negative 12. So negative 12 times 10 to the negative 9 coulombs. And we divide that by 0.04. And this is going to be whatever this is. So tell me what you all get. I got negative 2520. Do you all agree? Is anyone out there? Okay. Cruising right through this. I'm going to skip part B because I'm going to assume you can do the same thing that we just did. For part B, all you would do is you'd change the distance to A. Well, it'd be the same action. Now it would be 4. The distance to number 1 would be 4. The distance to the other one would be 14. Same concept. Okay. C, it's... Actually, I think C is 0. We'll do VC just in case. So for part C, the potential at C again is V1 plus V2. That's going to be equal to K times Q1 over... The distance between Q1 and point C is 13 cm plus Q2. The distance between Q2 and point C is also 13 cm. But Q1 is equal to negative Q2, right? Which means these are going to add to 0. So the potential at point C is equal to 0. In fact, the potential would be 0 anywhere along a line that's the same distance away from both of them. Okay? Does that make sense? Anyone have any questions? Okay, let's look at a problem that's a little bit more challenging. Did anyone have any questions? I didn't wait very long. All right, well, if you have a question, please ask. I'm not going to sit around and wait. Is C an equipotential? An equipotential in this case would be a line all along here. That would be an equipotential. Right there would be an equipotential. The line. Equipotential doesn't mean it has to be 0. It just means it has to have the same value. Okay? That's all that it means. All right, let's do one more that's a little more challenging. Also involves point charges. Okay, so moving through a potential difference. We have a dust particle with a mass of 5 times 10 to the negative 9 kilograms. I'll write that right here. 5 micrograms. Wait. That's not micrograms. Oh, wait, micrograms it is. Okay. And a charge of Q naught equal to 2 nanocoulombs. Why don't we just call it Q? Does it really need to be called Q naught? I guess we can call it Q naught. So this is 2 times 10 to the negative 9 coulombs. It's positive. It says it starts from rest, so we know that it has an initial velocity that's equal to 0. And because that's at point A, we'll call this VA. So VA is equal to 0. There's going to be some problems here with the V's. That's fine, though. Its initial velocity is equal to 0. It starts from rest, and it moves in a straight line from point A to point B. What is its speed V at point B? We want to find its velocity at this location. Given that we have positive 3 nanocoulombs, that's 1 centimeter away, negative 3 nanocoulombs, that's 2 centimeters away at the starting point, and then we're going from A to B, okay? So that's the question. What is the velocity at point B equal to? Now, because this problem involves velocities, we're probably going to have to use which equation to find those velocities? We used it earlier on in class. Not kinematics, kinetic energy. Kinetic. 1/2 mv squared, exactly. We're going to need to use this equation. Work done by non-conservative forces is equal to change in kinetic energy plus change in potential energy. And we know the change in kinetic energy is going to be something like 1/2 m times v at b squared minus v at a squared. These are velocities, right? Plus, what did I tell you to do with delta u? What do I replace the delta u with? What do I put down here? I only said it once, so I understand if you don't remember. You can look back through your notes, if you're even taking notes. I probably wouldn't be taking notes if I was having to look at a screen, but... Q delta V. So every time you see delta U, just immediately write Q delta V. Don't even think about it, okay? And then if you could do me a favor and put little lines above here to indicate that it's voltage and not velocity, it's kind of confusing, right? Because you have to... delta V squared and delta V. Put capital V, put little lines up here. All right, so what do we need to calculate then? We know what VA is. It's 0, right? Do we have the mass? We do. We have the mass. We have the charge, right? In our case, this is going to be Q sub 0. Let's be very clear here. This is Q naught, as it's the particle that's moving. This is always going to be the particle that's moving here. So what do I need to calculate to do this? We're solving for VB. We already know M. We know Q naught. What's left? Change in voltage. Yep. Delta V. Now, we just learned how to find the electric potential due to a point charge. So, what I'm going to do is, we are going to calculate, just kind of as a separate calculation over here, let's find the potential at point A, and let's find the potential at point B, okay? We know the potential at point A should be equal to K times Q, let's name these. Can I call this Q1 and Q2? God, they love keeping things like simple enough that it confuses people. Like Q1 is positive and Q2 is negative and they have exactly the same number. Like, would it have been that hard for the publisher to just make this -4 or something like that? Like, I don't understand why they have to make things... Like, they oversimplify things to the point where it makes it really hard to understand what's going on sometimes. All right, so it's K times Q1 over, we'll call this R1. Oh, we're going to have some problems now. Oh, we'll call it R1 anyway. You know what? Let's not even do that. It's Q1 divided by the distance from point A to where the charge is. And we can see what that is on the picture. It's 0.01 meters, right? Let's just plug it in. It's a lot easier to do it that way. Plus Q2. And now Q2, the distance from Q2 to A is how far? How far is that? 0.02. Yep. So we'll just plug in 0.02 down here. Okay. So that is going to be what VA is. Now you all can see what the values are, but I'm still going to plug them in here. I'm not going to rewrite K. I get really tired of doing that. Q1 is 3 nanocoulombs. So 3 times 10 to the negative 9 coulomb over 0.01 plus Q2 is negative 3 over 0.02. And we get an answer for that. Can you all calculate what that is for me? And then I'll write down what this one is. Come on, please let me just delete it. Okay, there we go. I think these just switch. Okay, what'd you get for the first answer? All right, and I'm willing to bet that this other one is negative 1350. I'm gonna check it myself, but I think that's what you're gonna get. Whoops, I made a mistake. Oh, negative 1350, right? Yeah. See, this is what's it's so frustrating. Like, there's so much symmetry that, like, whatever. So the potential at A is 1350. The potential at B is negative 1350. And we actually needed to figure out what delta V was. So just as part of our calculation here, we know delta V, you have to do final minus initial. So we'll take the potential at point B minus the potential at point A. So that's going to be negative 1350 minus 1350. See, it's like you plug them in. It's like, what did I even plug in? I plugged in this and I plugged in this. The minus sign is from there. It's really aggravating. I should have just changed the number. I don't know why I did it the way I did. So this is going to be double this. So that's at 2700. Negative. Is that right? Yes. I think it is. Okay, now we can solve our original equation. The work done by non-conservative forces is 0. There are no non-conservative forces in the problem. We rearrange that equation, and we're going to get that VB is equal to the square root of negative 2Q delta V divided by the mass. Same result we got earlier. Plug in our numbers, so it's 2 times our charge, Q naught, this was actually Q naught, sorry, was 2 nanocoulombs, so 2 times 10 to the negative 9 coulomb. Multiplied by delta V we found was negative 2700 volts. Throw an overall minus sign in front of this, divide by the mass. I wonder if this works out. It's 4 over 5. The 10 to the negative 9s cancel out. So it's 4/5 of this. So it's 0.8. 0.8 times 27. There's an, okay, maybe it'll work out, I don't know. Tell me what you all get if you calculate this. You get 46? Yeah, okay. That's what I got too. Okay, we're not getting cut off here, that's good. VB is equal to 46.5 meters per second. It's not very fast for a particle that's only 5 nanograms. Or was it, micrograms? Okay, very similar to the problem we did earlier. The only difference is we had to do this calculation before we could fully solve it. That's it. That's not really that hard. I mean, this is easy, right? It's easy. Is it easy? No. Nothing in physics is easy. But relative to other physics stuff we've done, is this easy? I don't know. Maybe it's moderately difficult. Do enough problems, you'll figure it out. Okay. Are we ready to do this one? Doesn't matter. We got to do it no matter what. I have to make sure that I tell you about this. 340. Okay. Solid conducting sphere of radius r has a total charge q. Find the electric potential everywhere, both outside and inside the sphere. So we have a solid conducting sphere. What do we know about conducting spheres? We spent a lot of time talking about this last week. Yeah, they're incredibly... Isn't it frustrating, Patrick? Isn't it frustrating how simple they are? I hate it so much. It was my biggest pet peeve when I was a student. It continues to be my biggest pet peeve as a teacher. I know I need to do simple examples. Ah, yes, Josh, that's right. It is a charged conductor, and therefore we know that if it carries a charge Q... you're all saying all the right stuff. That's good. We know that it's an equilibrium. All the charges have to go straight to the surface. And we know that the electric field is equal to 0 inside. That's the most important part of this. The electric field is equal to 0 inside, right? It tells us the total radius is r, so I'll go ahead and label that this is r. We want to find the electric potential everywhere, both outside and inside the sphere, okay? So let's start outside of here, okay? Now, we know how to find the electric field for an object like this, right? If it carries a charged q, we know that for r greater than r, E is equal to kq over r squared. Okay? We know that this is true. That means that as long as we're anywhere outside of the sphere, this is our electric field. It behaves like a point charge. Therefore, we can use the same derivation we did for a point charge to find what the electric potential is, and it will have the same answer. So we know that for r greater than big R, when you're outside of the object, this is what the value of the electric potential is, okay? Because it acts just like a point charge for r greater than r, right? What about on the inside? Now, this is the part that's it's simple, but it's not simple. Pick any 2 points, A and B, between here and here, right? Move between points A and B, and ask the question, what is the work needed? The work done by the electric fields along line AB. What's the answer going to be? The electric field's 0, right? So it's 0, right? This is equal to 0. Well, we said before that work is related to the negative of the change of potential energy, and the change of potential energy is negative Q times delta V, right? So if the work done is equal to 0, then delta V has to be equal to 0. So that's the answer. For R less than R, delta V is equal to 0. And that's not really the answer, though, right? Because it says to find the electric potential, and this is electric potential difference, right? Electric potential difference. So now what we have to do is we have to go to the point where these two have to meet up with each other. So if I come to a point right on the surface right here, I know as long as I'm outside the surface, the value of the potential has to be this, right? So on the surface, the value of the electric potential, and this is going to look, if you don't think about it, it's going to look like the same equation. It's not the same equation. This is the value of the electric potential on the surface, right? What's the difference between these two equations? It's just the r. Here, little r is like a variable. Little r could represent any distance r, okay? On the surface, I'm saying on the surface, little r happens to be equal to big R. So we plug an r here, right? Now, if I tell you that the electric potential on the surface is equal to this, and I tell you that the electric potential at any 2 points inside has a potential difference of 0, right? What if I take this, my line here, and instead of drawing it between 2 points inside my surface, what if I extended it all the way out to the surface, like this? Well, now, delta V still has to be 0, because the electric field all inside was equal to 0, right? So what that means is that this is also the electric potential on the inside. So when you have a charged conducting sphere, the electric potential inside is constant. It has to be, because if the potential changes, there would be an electric field, but there's not. So the electric field inside has to be constant, and the only possibility is that it's equal to the value on the surface. Now, those of you that had a lab where you had a card that had a ring on it, and you looked at the ring, right? And you measured the electric potential on the inside with your voltmeter, and you measured the electric potential on the surface with your voltmeter. I think all of you said that you were kind of surprised that if it was 6 volts out here, it was also 6 volts in here, everywhere. Do you all remember that? I'm talking about the lab now. Yeah, right? Now, not all of you had a ring, right? But I think every one of you that had a ring noticed this, from what I could tell. That if it's 6 volts out here, it's also 6 volts all throughout here. It has to be, okay? Now, I know for a fact you have some homework problems where there's like a ring with a hole cut inside of it, okay? Same concept. The electric potential on the inside is going to be uniform and equal to the value at the surface. Whether it's a ring, or whether it's a disk, or a sphere, or whatever it happens to be. So keep that in mind when you're doing your homework. This is important that the electric potential inside is equal to the value on the surface. Does anyone have any questions? This is just a conceptual idea. This problem isn't really a problem. It's just a problem to teach you this idea right here, basically. Teach you this one idea. Do you see the connection between V constant and electric field 0? If V changes, like if you go from 10 volts at one position to 8 volts at another position, there's an electric field there, right? Do you all agree? Like if I tell you that I have a place, and I tell you that the value of the potential is 10 volts, and I have another place, and I tell you that the value of the potential is 8 volts, it's required there must be an electric field between these 2 points. And I know that it points from high to low. It's required. So the only way the electric field can be 0 is if the entire object is like an equipotential surface. If it all has the same potential. Because any difference in potential produces an electric field. Any difference. Right? Any potential. It's like saying that I can create, this is what it's like actually. So, get this thing to stop wobbling. I can create a flat surface along which the elevation is the same everywhere, right? But the moment that I tilt it, right, and I have a difference in elevation between one point and another point, there's automatically a gravitational field that's set up, right? I tilt this, boom, gravitational field set up, and the object slides, right? I keep it flat, the elevation is uniform, so there's no gravitational field experienced by the pen, right? You only feel the gravitational field when you tilt it, right? It's only when you create an elevation difference between 2 points, right? You could think about this as being like 10 volts and 8 volts, right? Whereas when it's level, it's like 10 volts here and 10 volts here. Okay, so the inside of a conducting sphere is like a flat surface. I'm sure the flat earthers would be happy with that I can compare a sphere to a flat surface, but the inside of the sphere is like a flat surface for electric charges. An electric charge that was placed somewhere inside of this surface here would feel no force. Just like this pen feels no force until you create a gravitational field by creating a potential difference between the ends, by creating an elevation difference between the ends. Okay, I probably said too much, but hopefully some of that kind of got through to like maybe 1% of you. Does anyone have any questions? All right. The next thing we want to do is to look at the connection between electric fields and electric potentials. Have we done... All right, this is the last problem. We do not have to do this problem today. This is purely conceptual and it's not important. We can do that problem next time. It's not going to have any effect on... So the next thing I want to do is to learn how you go from electric potential to electric field. We found how to go from electric field to find electric potential. Now we want to do the first. We want to go from a known electric potential and then find electric field. This is actually very easy, as it turns out. Yes! That's exactly right, Josh. An electric field can only exist between a potential difference, correct? That's correct. Just like a gravitational field can only exist between what? You have to have an elevation difference, right? The top of a surface of a table is like a flat surface that doesn't have a gravitational field. The moment you tilt the table, you create a gravitational field, basically, or you subject it to it. Okay, from a known electric potential, to finding the electric field. How do we do this? So we're going to start off with the simplest thing that we have from the beginning, which was that for a uniform field, we said that delta V was equal to something like negative EX times D, right? But really what we meant by this was something like delta V is equal to something like negative EX times delta X, because the D was really a displacement, right? What we're going to do is say, what if we want to look at infinitesimal changes in the electric field? Or infinitesimal changes in the electric potential? We can write this like this. And then we can rewrite it like that. And that's not exactly the answer that we're looking for, but it's almost there. This tells us that if I know the electric potential as a function of x, I can find the electric field as a function of x by just taking a derivative, right? And in general, what we can do is we can expand this to 3 dimensions. So if I want to expand this to 3 dimensions, I'm going to have to write 3 different equations, and they're going to look like this. Because we're going to be working in 3 dimensions, and because the function v may be a function of x, y, and z, so we're going to assume that v is a function of x, y, and z, or some other variables, that if I take the partial derivative, we call this a partial derivative of the potential with respect to x, you get the x component of the electric field. If you take the partial derivative of the potential function with respect to y, you get the y component of the electric field with a negative sign. And if you do the same thing for the z direction, you get the z component of the electric field. VV, okay. Now these del's, I say del instead of delta or d, these del's mean that we are doing partial derivatives, which you may or may not have been exposed to yet, I don't really know. Those of you that are really familiar with 220, can you tell me, when do you learn about partial derivatives? Or do you learn about them in Calc 2? It's Calc 3 probably, right? 220? I'm just curious, if you're taking Calc 3 right now, or Calc 220 right now, have you seen this yet? Those of you that are currently taking 220, have you seen this yet? I'm just curious. It's like halfway through, so probably not. Probably not. Well, that's okay. Basically, we've now gotten to the point where we've covered pretty much all the math that shows up in Calc 220, so it's good that you haven't covered any of it yet. That's totally normal. Maybe we need to just reorganize the physics series so that, I don't know, we learn about circuits first and learn about this stuff later. Maybe that would line up better with your Calc 3 series. I don't really know. Regardless, let's talk about how we do this. So, let's say that I give you a potential function. We'll use a really simple example. And let's say that it's 5x squared z plus y to the third x over 4 plus z cubed or something like that. So I give you this function, right? And this is my potential, okay? This is the electric potential, which means that we have to have some kind of like things in here to make the thing work out right, the units work out right, but we're not going to worry about that for now. Let's just see how we actually apply these functions over here. According to what this says over here, I can find the x component of my electric field by taking the partial derivative of this function with respect to x. What that means is you basically take all of the variables that are not x and you treat them as if they were constants. So with looking at this first term right here, we're going to treat a 5, that's obviously a constant, right? And the z, we'll treat those as constants, so we'll just ignore them. And then we take the partial derivative with respect to x. So the partial derivative with respect to x of x squared would be just 2x. And we have to drop a negative sign in front of here too. Plus, we look at this term right here, it has y cubed over 4. Those don't contain x's, so we just leave those alone. It's a constant. And then we take the derivative of x, which is just, 1. And we put our negative sign in front of here too. Plus the derivative of this term, if z is a constant, then the derivative with respect to x is 0, right? It's a variable, but we're doing a partial, so it's basically the same thing. When I take a partial derivative of z cubed, you just get 0. So all told now, my electric field for this particular function is negative, what do we have? 10xz minus y cubed over 4. That would be my x component for my electric field. And we can go through and do this for all of them. If we do the y one, the first term, what's the partial derivative of this term with respect to y going to be? So ey is the partial with respect to y. It's 0. What's the partial derivative of this one? X over 4 we treat as a constant. You get 3y squared from here. So I'm going to say that this one is going to be 3 over 4 times x times y squared. And then again plus 0. So that means that ey is equal to negative 3/4 xy squared. Does that look right to everyone? Did I make a mistake? So you guys get the idea. If you know how to do derivatives, you basically know how to do this. The only thing you have to understand is that if you have x, y, and z, when you take the partial with respect to x, the partial derivative with respect to x, you hold y and z constant. When you take the partial with respect to y, you hold x and z constant, and so on and so forth. So it's not super complicated. In fact, I'll leave doing z for you. So there's no such thing as a product rule. You could still have a product rule, but you don't have to do it like maybe what you're thinking is. I mean, I could still have, if I told you that, just for example, if I said that v was equal to x, y, sine of x or something like that, you'd still need to do a product rule for this. Just to show you, if we did negative del v del x here, you would get negative something like that, right? So you still have to do the partial. You still have to do the product rule, yeah, and you still need to do the chain rule and all that kind of stuff. But you just treat y as if it was just a number, basically. That's really the only difference. It's not super complicated. Okay. All right. So this is really powerful, and there's a lot of things we can do with this. I don't know that I have a lot of time to show you all the things that we can do with this. I did already cover, I think I've covered all the topics that I really want to cover, so I think we have time. These last few topics aren't incredibly important, but I'm going to show you a really simple example of, it's not simple, I'm just going to show you an example of how this works, just to prove to you that it works, okay? And we'll just use, I would use one of the other things we would drive, but I'm just going to use a point charge for now. So we know the electric field of a point charge, right, is kq over r squared, right? We also know that the electric potential, this is for a point charge. We know that the electric potential for a point charge is kq over r, right? So, is it possible to go from this equation to this equation? And I'll give you two different ways you can do it, okay? The first method would be to just say, well, I told you that you could find the x component, right, by taking negative del v del x, right? Well, what if you want to find the r component? The radial component, you should be able to get that by just taking negative del v del r, right? I mean, why not? Seems reasonable. If ex is del v del x, why can't er be del v del r? That'll work as long as you're doing spatial derivatives. If you start doing a derivative with respect to an angle, there may be some other terms that show up here. Like if I want to find the theta component of the electric field, I can't just do del v del theta. I think I have to do del v del theta times 1 over r sine theta or something like that. I don't really know. But as long as it's a spatial derivative, we can totally just do this. So let's check. If I take del r, negative del r of kq over r, what do I get? What's the derivative with respect to r of kq over r? It'd be kq over r squared, right? With a negative sign. But then negative times negative, this actually does give you the r component of the electric field. It's exactly kq over r squared. That's nice. But you already knew that. That's not that surprising. Well, what if we wrote it in a more complicated way? Just to prove to you that this really does work, what if we wrote it in a more complicated way? So let's try it a different way. Let's see if it works too. So if I take V is equal to KQ, and I let R be equal to this. That's what R is after all, right? Defined from a coordinate system, that's what R would be, right? If I use this definition, can we find the X component of the electric field now? That's something we didn't even know how to do before. Well, we did, but we couldn't have defined it all over space. Let's see if we can do that. So let's take this, and let's see if we can find what the X component of the electric field is. So what do we have to do? We have to take the negative partial derivative of this function with respect to X. That's kind of a little bit of work, but we can do it probably, right? So what's our function? It's KQ over the square root of all this junk, right? What's the derivative of that going to be? We just have to, what, subtract 1 from the power? I would argue that it's something like this. But we have to multiply by, so I've subtracted 1 from the power, right? So we go from -1/2 to -3/2. It's the denominator. We also have to multiply by the derivative of the inside, which is 2x, and we have to drop a minus sign on there. Oh, but wait, I left something out, right? I also have to multiply by the power. So I have to multiply all of this times -1/2. So there's a negative sign here, but we also have to multiply by -1/2 from the derivative. So we end up getting KQX over I think that's right. Does that look right to everyone? We're basically doing like KQ over U to the 1/2, which is the same thing as KQ U to the -1/2, which when you take the derivative of this, you get a -1/2, that's this. And you have KQ U to the -3/2, that's this. And then you have to multiply by the derivative of the inside, which is 2x from the chain rule. So we get this KQX over this. Now that we've done it for x, and because x, y, and z all show up as, they're all the same, right? We can probably, they're symmetric. KQY over x squared plus y squared plus z squared to the 3/2. That's going to be EY. And then EZ is going to be equal to KQZ over x squared plus y squared plus z squared to the 3/2. So now that we have EX, EY, and EZ, that's kind of nice. I mean, this actually gives us a general way to define what the electric field X oh my god, the whole thing that I'm writing is off the screen. I'm so sorry. There we go. That's kind of nice. This gives us a way to find the electric field X component, Y component, and Z component if for whatever reason you ever wanted to, using coordinates. Like, I don't know, if you were designing a video game or something and you had to plug in something to represent a force field of some kind, and you wanted to do it in Cartesian coordinates, this is how you would do it. But we can see something else here. The electric, this also I hope will help you a little bit with just vector stuff. We know in general that any vector, like the vector for the electric field, should be equal to this. Right? I can write any vector like that. It's going to have an I hat component, that's EX, a J hat component, that's EY, a K hat component, that's EC, right? The X component, Y component, and Z component of the field itself. If I take those three equations and I put them together, I'm going to do a little bit of math here in my head because I think it's required. We're going to have KQ common. All of the terms also have in the denominator x squared plus y squared plus z squared to the 3/2. So every one of them has that, right? Multiplied by, now what we're going to have is there's going to be an xi hat plus a yj hat plus a zk hat. So that's our definition of the electric field now. That's the whole electric field. And we got it by just taking derivatives, which is really powerful, by the way. what we're going to learn as we go through this class, it is often very easy to define electric potential. It is often very hard to define electric field, but if you can define this very simply, then you can easily get electric fields. So we get this expression right here. Now the question is, how does this compare? Okay, is this the same thing as this? Is this the same thing? Is this the same thing? And I would argue that it is. And the reason why is because this thing in the denominator, x squared plus y squared plus z squared, is the same thing as r cubed. And this piece right here, that's how r is defined. And going from here to here is just one step, because we know that r over r is equal to r hat. Can you all see that? I did that very fast. Xi hat plus yj hat plus zk hat is r. That's r. That's like, you know, if I tell you in a three-dimensional coordinate system, I pick a point here and I tell you that it has coordinates x, comma y, comma z, right? Then it creates a vector that we would draw from here, and that vector is what we call r. And r would have components x, I hat, y, j hat, z, k hat. Okay. Like I said, x squared plus y squared plus z squared is r squared, but it's to the 3/2 power, so that's r cubed, and then it just naturally just. So it's I think that's really fascinating. That you can take a function by taking derivatives, you can get this answer. Now to expand this a little bit farther, what we can do is there's another way we can write this in a more general way. So we're going to say, let this symbol, draw a little vector symbol above it, let this be equal to this operation. Okay, so we call this an operator. What name do you all give this to in your calculus class? Don't say gradient. What name do you give to this thing? Don't say gradient, whatever you do. What's the name of this operator? Dell Operator? Okay. Call this the Dell Operator? That's fine. I remember learning it as the Nabla. Have you ever heard Nabla? Was that just my weird school that they called it Nabla? Yeah, Nabla. It's spelled like that. You have heard that? Okay. Doesn't matter. Dell Operator, I prefer this. This is way better. The Dell Operator. It's an operator. It doesn't have any meaning in and of itself, right? But what you can do is you can say that the electric field is equal to, and this is where I'll use the word gradient. When I apply this to a scalar field, so the electric potential is a scalar field, then we call this operation the gradient. There needs to be a negative sign in here as well. And that allows us to say that the size of my electric field is negative of del x of v I hat plus del v del y j hat plus del v del z k hat. And that is the more general version. Or put in a very simple way, it's equal to the gradient of v. We call this grad v sometimes, is what they say. Gradient of v. Okay. What does the gradient do? It tells you the direction of the greatest rate of change for your function. Or, for your function. So for a scalar function, the gradient tells you the direction of the most rapid rate of change of your function. The way I think of it is, if you have a hill, the gradient tells you the direction that a ball would fall if it was falling along the hill. This may be something that in your 220 class they may have talked about now. The topo lines. The gradient would be, at any point on this picture, the gradient would represent an arrow drawn, for example, in this direction of the place where the slope changes the fastest, okay? And that gradient may go this direction here, and then this direction here, and then this direction, this direction, this direction, then it may go this way, then it may come down this way. I don't know. But it's the place of the greatest rate of change, which is going to be the place where the lines are the closest together, and it would indicate the direction that a ball would fall if it were to roll down from that position. That's what the gradient is. And you get it by taking this function and multiplying it by your electric potential. All right, I think we have 10 minutes left, right? We get till 4:20? Yeah? If I'm wrong, tell me I'm not. Okay. So one last thing. Oops. So to repeat a calculation we've done before, but using it for potential, we want to find the electric potential for a uniform line of charge. So this one's a little bit easier than the one we did before. And with the amount of experience you all have with this stuff, I suspect this will be quite simple for you. So we start off with a line right here. And this line, I don't know if this is going to let me interact with this at all. Okay. So we have the line. It carries charges. We'll say somewhere here in the middle that this is going to be y equal to 0. We'll call this y equal to plus a. We'll call this y equal to negative a. We have a positive line charge here. We're going to find the electric potential at a point over here, P, that is at a point in the middle. So we're going to need to draw some lines right here and indicate some things. So I'm going to draw a line from here to here, and we're going to call that distance x. And then I'm going to say, take my object and break it up into tiny little pieces. Hopefully this will help you to remember what you're supposed to. So I'm going to take my object, I use a different color. I'm going to break it up into a tiny little piece right here. So I'm just looking at one little piece of my object. I'm going to say that the amount of charge contained there, we're going to call dq. We're going to say that the height of this little piece is d sub y, where we can make the representation that dq is equal to lambda times dy, where lambda is the total charge divided by the length, so we'll call it capital Q divided by 2a. So I basically say total charge is Q. And then what I'm going to do is say that we can find electric potential now for this object by taking an integral of k dq, k dq over r. The only difference here is there's no r squared that shows up right here. That means that I need to draw one more vector here, or a line, no vectors in this problem, that goes from here to here, define that to be r, define this to be theta, and I think we're good to go. Now what we say is that at this particular location here, P, the size of the electric potential at P, we could call dV. I'm not drawing any arrows or vectors because the electric potential is just a scalar. The potential at that point should be K times dQ divided by R. And all we need to do is to find a way to replace variables so we can integrate over the entire object. Ideally, we'd probably want to get something in terms of y or theta or something like that. So we do replace dq with k times lambda dy over r. And now we have y and we have r. And we need to probably do something about getting a theta in here somehow or something like that so we can integrate over this. Or we could just write r in terms of y maybe. That might work. So we also know that r is equal to the square root of y squared plus x squared. That's the right angle. If we plug that in here, we're going to get the integral of k lambda dy over square root of x squared plus y squared. Is this an easy integral to do? Is this one where we want to do a trig sub? Looks like a trig sub. I can usually do u subs in my head. I can't do trig subs though. Right, make that substitution. Let y equal to x tan theta, dy equal to x secant squared theta. Then we end up getting integral k is all equal to v. K lambda dy gets replaced with, and the denominator becomes square root of x squared plus x squared tan squared theta You asked earlier, Kavi, are we going to have integrals like this on the test? Probably not. Although I think this integral is kind of easy to do, to be honest. So if I gave you a problem like this, and I said you need to work it all out, I would say something like this. I would say this might be a helpful substitution, right? Or something like that, right? I'm not going to waste a lot of your time during the exam of you just trying to solve integrals. That doesn't mean there won't be integrals on the test, but they should be relatively easy to do. And if they're not, I will give you the formula for what you need to do to solve them. Okay, so we do this. We've changed our variable to theta, so we'll have to figure out what the limits are. We can do that later. I think this should work out now, because now I think what we're going to get is the integral of k lambda x. There's still a d theta here I left off. We still have secant squared theta d theta. But the denominator should become something like 1 plus tan squared. Is that equal to secant squared? That sounds right, yeah. So we're going to get that times secant theta. Oh no, are we going to end up with a secant theta in our problem? Don't like to see that. Makes me think I did something wrong. Did I do something wrong? And if we get secant theta as our answer, that's not exactly a... We haven't actually made our lives any easier, right? Could be the case. We're supposed to just look this one up. I don't know. But it looks like what we get is... Yeah, that's what the answer is. That's right. I mean, that's what you would get. I just don't think that's the right answer. But maybe it is. Maybe this one does have a natural log in it. I think it does. I think it does have a natural log in it. I think that's okay. I think it's okay. Anyway, so you're saying this is equal to k lambda. What is it? It's the natural log of the secant of theta plus tan theta, right? Yeah, it's the same answer. I agree as that problem. But I just don't know. So now we're going to have to go from basically the theta at the top to the theta at the bottom. I'm pretty sure that's going to be... So when theta at the top would be basically the arctan of a over x. So this is going to be the arctan of a over x, and then at the top up here, and this will be the arctan of negative a over x. And that's what we have to plug in here. So maybe the thing is that with the way this is defined, these numbers actually kind of tend to make sense. Because now what we have to do is we have to draw those triangles. How much time do I have left? Are we over time? No, we actually have time left. Okay. I was gonna say we can finish this up another time, but take two new triangles here. The size of this is a, negative a. This is like our theta, and this is like our negative theta for our limits. And secant theta. So if this is a and this is x, secant theta would be r over x, right? And tan theta is just a over x, right? So I think what we get is k lambda times the natural log of secant theta should be r over x, and tan theta should be a over x. We can rewrite r in terms, r is equal to square root of x squared plus a squared. If we need to, we can do that. Minus the natural log of the secant of negative theta is still going to be r over x. But the tangent of negative theta will be negative a over x. Does that look right? Does it look like I did that right? The idea here is that the secant of theta, and theta is the angle whose arctan is a over x. So that's why this ends up just being r over x here. So then this actually simplifies quite a bit, doesn't it? Because now if I have a difference of logs, that's like the log of the ratio, right? Which means all the x's cancel. I think you're going to get, I'll put the step in here, r over x plus a over x divided by r over x minus a over x. So all the x's cancel, right? So we end up getting that. I think that's the right answer, actually. I mean, I'm not sure, because I haven't done this problem in a year or so, but I think this is the right answer. I'm just going to check, because I'm just really not sure. I don't want to tell you something that's completely wrong. So this is toward the end. Maybe it's toward the middle. Yeah, well, we have the r minus a thing, but it is natural log, oops, it is natural log of rb over ra. So for us, is this the same thing? R plus a over r minus a? What was their integral? Oh, they used a different method of doing this, didn't they? They didn't use the same method that I did. Huh. RB and RA. Something wrong with what I did. I feel like something's wrong here. I think you should not take anything that I did here as being accurate. And I don't know what I did wrong. Other than to say, to get the answer that they picked, oh yeah, that's the problem. That's what the problem is. I would need to replace R with this, and then I could probably prove that if I take a difference that you get the same answer. That's what would happen. So I think they say the same thing, but there's something very confusing about putting an R in here, and it means something different than what they've done. So you should compare to their answer for the real way to do this. I don't think that means this is wrong, though. It just means that I need to write this in a different way. Anyway, I don't mean to be too confusing. Sometimes I try to do things my own way, and it doesn't work. So you have to write this as natural log of the square root of r. So r was x squared plus a squared plus a over square root of x squared plus a squared minus a. That would be in the potential at a point x. And what you'd need to do to get the answer they have, you'd have to find the potential at like point x1 minus the potential at some point x2, which would be like k lambda natural log of all of this stuff at two different points. Copy, paste. Is it going to do it? I don't know. Well, we're over time, so I'm not going to sit around and fumble with this, so yeah. The next one over? No, I wasn't. This is the right problem. It's this one right here. It's correct. It's just that I could have done it in an easier way if we'd just done this method. So what they did was they just took just to show you, they just said use this definition, use the e.dl. Since we already know what e is here, then you do the dr over r, and you just integrate, you just end up getting natural log. Yeah. So I did something to make this more complicated, which was that I treated it similar to the way they solve a lot of the other problems, and I just didn't review this particular problem before class, so I didn't realize that that was the easier way to do it, although now it seems really obvious. But in some sense, this probably reduces down to what they have, but it still won't let me copy paste. Like, it won't let me interact. Like, the whole thing is frozen up now, so can't do much. We got to just stop. So that's that. Again, we have an exam on Wednesday. I've already told you all the information you need to know about it. It covers chapters 21, 22, and 23, up through what we did in class today. So if there's anything from chapter 23 that we didn't do in class today, it probably won't be included, but I think we covered everything. Yeah, we did. We covered everything. Definitely be worth your while to read chapter 23 as well. It's kind of long, but I think rereading the chapters helps. 21, 22, 23. Coming to office hours tomorrow, asking any final questions you have about homework helps, all that kind of stuff. But again, 1:30 or 1:15 on Wednesday, show up to the same place you showed up for lab, and we'll probably be in rooms 108 and 109, and I'll split you there. You will have, as soon as I finish writing the test, so I haven't written the test yet. I mean, I have, but I haven't finished it. I wanted to see how far we got in class today, and so now that I see we've covered all of 23, I feel pretty comfortable putting problems in here from chapter 23. I hope that you all didn't think today was too complex. It's just a new idea, electric potential, and it's a way of describing the energy per unit charge. It's important that you distinguish between electric fields, electric forces, and electric potential. So I'm just going to, as a way to end, how many questions are going to be on the test? I don't know, 50. Probably more like 4, honestly. So just keep this in mind. There's these 3 different things that you learn about in this class. There's 4. They all start with the same word, electric. And I'll just give it to you in the order that we learned them, right? Electric charge, right? This was Q. This is how many electrons do you have or are you missing, right? Electric force. This is, for point charges, KQ1, Q2 over R squared, right? But I think someone pointed out early on, you have to take the absolute value of the charges here, and you've got to figure out the direction of the force for yourself. We next learned about electric fields. For a point charge, the electric field is KQ over R squared, right? Keeping in mind that the connection between electric force and electric field is that electric force is given by electric fields times Q. And what we learned about today, electric potential, is given by so they're all different. They're all different. Charge, force, field, potential. Just make sure you understand the difference between these. Oh, I know what we didn't get to today. So you're going to have problems on your homework where they give you multiple point charges, Q1, Q2, and Q3. And they're going to ask you what is the energy of this system? I forgot about this. I was thinking about it while we were going through it, and it's listed on my list up there. I just forgot about it. I'm just going to tell you real quick that to find the energy of a system like this, you need to know the distances between the charges. If you call this R12, R13, and R23, I'm telling you this for your homework. Because I didn't remember to talk about this today, I probably won't put it on the test, but it will show up on your homework. To find the energy of this arrangement of charges, you just take all the possible combinations. You go K, Q1, Q2 over the distance between those two, plus K, Q2, Q3 divided by the distance between those two, plus K, Q1, Q3 is the one I didn't do, divided by the distance between those, plus ... for any combination that you can find. This is something you will see show up on your homework. I just forgot to get to it today. Would have been more useful than blathering around about that last problem I did, but such is life. Can't go back in time. So just keep that in mind. I probably won't put that on the test, but you will see it show up on your homework. Okay. That's all I got for you today. Sorry for going over. It's just trying to catch up to where we're supposed to be. Anyway, I will see you all on Wednesday. I hope you guys have a great day. Again, I have office hours from noon to 1 tomorrow.